Hello! Today we're going to talk about differential protection and how to test it with DRTS using the software TDMS. In the TDMS software, the latest version 7.21, we're going to choose differential 87 and then 87T. Clicking here will open the necessary application, and of course there are a few different ways how to start this testing. You can also choose a relay, which is mentioned in our library of differential relays, or you can simply import RIO or XRIO file if you have it from your relay. But today I'm going to talk about, let's say, the most difficult case where you don't have any of these, and I'm going to show you step by step how to introduce the parameters and how to start testing. So the first thing we would need to do would be to set the vector group of our power transformer. So our journey starts here. I'm going to click here, and then I'm going to choose my transformer. Today I'm dealing with a transformer which is YD, and you can see here that you have all types of vector groups: YY, YD, YZ, delta Y, delta delta, and delta Z. So I'm going to click here to choose YD, and since my transformer has two windings, I'm going to write here the nominal power of the primary side, which is 50 MVA, and the nominal power of the secondary side, which is also 50 MVA. My primary side voltage is 132 kV, my secondary side voltage is 18 kV, and the vector group I need to finish with the number. So in my case I have YD11, and I'm going to choose number 11 here. If I had a YND11, so if I had my star grounded, I would click this, but since I don't, I'm just going to click OK. And before I click OK, I call you just to observe this. This is now YY0 because this is a default value. And when I click OK, this will change to YD11. So that's our first step, and we can see also that the power, nominal power, and primary and secondary voltage are here. Then the next step would be setting the ratio of our CTs. On the primary side, my CT is 250 to 1, and you can see that you can choose a YCT or a delta CT, YY or Y delta. In my case, I have a YY. While on the other side, I have, on the secondary side, my ratio is 1500 to 1, and it's also a YYCT, so I'll click also here. I'm going to add one more thing, even if I don't have it. If you were to have earthing, you would be adding it here. So if I were to add it, it would look something like this, but since I don't, I'm going to remove it. You can of course do the same thing on the other side, but you can also, if you have interposing transformers, you can add them here or on the primary side. You will choose your type of a transformer, you will write here your ratios, and you would proceed. In my case, since I mentioned that I have no interposing transformers, since I have a numerical relay, all this compensation will be done inside the relay. And actually, relay is the next step we are going to. I'll click this, and then I need to set some other values regarding the relay itself. First of all, internal phase and zero sequence compensation. This parameter you would need to read from your settings. In my case, I have it on the high voltage side. And my reference winding. Now, reference winding in my case is the low voltage, because for the relay I am testing right now, which is our demo relay, which is a protector relay, there is a rule that the reference winding is the first delta winding. So in our case, since we have YD11, the first delta winding is the secondary side winding, and that's why I'm putting the reference winding to be low voltage side winding. For the reference winding, if you're not sure, you should check the manual of the relay you're testing. The rules would be the first Y winding, the first delta winding, like in this case. In some producers say that it's always primary and rarely maybe secondary side. But in general, this is a parameter which if you don't know, you would have to check in your manual, and once you know that, for one producer, it's the same for all the relays from that particular producer. The next step would be phase sequence. In my case, it's ABC. And also very important parameter, CT star point grounding. In my case, it is as it is here, towards the line on both sides, primary and secondary. So by clicking OK, I'm now going to set my relay. The third step I will do is something which most of you will not have to do here, and that is this part here, which we called predefined transformer taps. This name could be slightly misleading, because actually what we're talking about here is magnitude compensation. So magnitude compensation, if you are dealing with any relay except GE and protector, you will just leave this as it is. But in my case, since I'm dealing with my demo relay protector, I am going to write here the numbers which I've calculated before, and for the primary side it's 0.361, and for the secondary side it is 0.547. For GE relays, you can find the necessary formula in the manual. So now we have actually set here the first tab, and we are now going to the second tab, which is relay characteristic. Now, relay characteristic, we have many of them. You can define them point by point. There is single slope, there is dual slope. We also have dual slope with knee point, railroad dubia, and also GE T60 universal relay type curve. In my case, we are dealing with a double slope relay, and again, these settings need to be checked in the relay you're testing. So the first thing would be pickup current. In my case, it's also 30% of nominal current. Slope 1 has 25% of inclination. Slope 2, in my case has 200% inclination, and the base point is 2.5. After that, OS, the knee point number 2 is 0, and in my case, maximum IR and maximum ID are set to be 8. Another very important element is the formula of restraining current. So in my case, it's actually IR equals absolute value of I1 plus absolute value plus of I2 divided by 2. And with this, I have set completely my characteristic and also my transformer in the step previously. Now I'm going to proceed with the test. First thing I'm going to do, I'm going to connect to DRTS, and I have here DRTS 64. So clicking OK, I will see that this element here from not connected changes the symbol and becomes connected. And right now I'm going to change from the tab system to tab test settings. The first and the most basic test you can do is by doing a click and test. We choose click and test, we click OK, And let me now explain what do we see in front of us. First of all, I want to comment on the characteristic here. The yellow line is the actual characteristic, while the orange lines are margins. So, easily put, everywhere below this orange line we should not have any trip, and everywhere above this orange line we have to have a trip. If this doesn't happen, then we have a fail. Now, in order to do a click and test, we first choose on which side we expect the fault to happen, on the primary side or on the secondary side. The fact that the curve changes is a normal. So on the primary side, let's do first test on L1. So on phase 1, I'm going to move my cursor and I'm going to click first here below the yellow line to generate a value. This is a message you will always get before starting the test. You need to generate the pre-fault values. Click no to change them. I'm satisfied with my pre-fault values. I'll click yes. And right now we will generate the first current. Before that, we need to be sure that currents 1, 2, 3 on the DRTS are connected to the primary side, and currents 4, 5, 6 of the DRTS are connected to the secondary side. If I confirm this, the DRTS will generate certain set of currents, and we will see that we had a timeout, which means the relay did not trip, which is what we actually expected. Again, the same we would expect if I were to click here, the same if I click here, and the same if I click here, because we are all the time below the orange line. Now let's see what happens if I click above this orange line but still below the yellow line. I would still expect no tripping, and that's what I'm getting. So all the tests we've done until now, we didn't see any trip. Now I'm going to change, and we see that by looking at this, it says timeout. The maximum time would be 1 second, which is plenty to see the relay trip, because we know that for differential relays the tripping time is 0. Now if I click, let's say here, let's see what will happen. So right now my relay tripped in 57 milliseconds. Of course, I would expect the same thing to happen if I were to click here, which it did, and here, which it did, and also let's try here, here, and here. Now this actually shows me that for phase 1 and the fault on the primary side, my relay trips correctly. Of course, we can now proceed and do a similar test for phase 2. So let's do a quick one. Let's just do one here and one here. And we see this one had timeout and the last one had a trip. The same we would expect for phase 3. So let's first click here. We have 57.8 milliseconds trip, and clicking here should give us timeout, which it did. We can now proceed with B phase faults. So L1, 2, we can do a quick test generating a fault here, and we see a trip, 57.6 milliseconds, and also clicking here would give us a timeout. Phases 2, 3 and 3, 1 would give us the same result, so let's move to L1 to 3. Let's click here, and we see a trip in 39 milliseconds. Trip here would also be expected in 60 milliseconds, while here we do not expect to see a trip. While I'm moving my cursor around this characteristic, you can always see here what are the currents, how do currents change. So actually, as I am now doing a three-phase fault, all three currents change. But if I go back to a single-phase fault, you will see that not all currents change, just some of them. So this is how you would do the most simple test, which is click and test. I forgot to mention one thing here. Of course, you would need to set your contacts, whether they are dry or wet. I am right now using C1 to stop the generation, and it's a dry contact. So that would be the test on the primary side. Let's do a few tests on the secondary side to see if this works. So phase 1, and we have a trip, and here we would expect a timeout. Then let's try now phases 2 and 3. Let's see if we get a trip. We did. And also here we got a timeout. Last but not least would be L1 to 3. One click here and a trip in 39 milliseconds, and one click here and a trip in, or no trip, a timeout. Another way how you could set the values, let's say you want to click here, you want to generate this combination of currents. Of course you can click here, but you can also say, you can see that this is three times differential current and 2 restraining current. So we can also say here 2 and 3, and I can click add to list, and right now I got my test executed, as you can see here, and the tripping in 63.4 milliseconds. Just a short comment regarding the tripping time. This relay is not, let's say, top of the line right now. It suffered some blows, so it might be that the tripping time is not what we would normally expect, like between 20, 30, maybe 40 milliseconds. Here we get something between 30 and 60 milliseconds, but this is just the characteristic of the relay I'm testing right now. Now, I would like to move on to the next test, and in order to do that, I'm going first to store all tests by pressing this button. Yes, I want to transfer all results to test table, and I can see that test table here. So here in results I have 29 tests which we have executed on phases L1, L2, L3, L1, 2, 3, and again on the secondary side L1, L2, 3, and L1, 2, 3. Going back to the test tab, we're going to move on, and I'm going to show you how to use another test which we call the verification of the curve. Verify curve is pretty useful test because actually it uses an algorithm which will automatically find for you, or let's say verify for you, the nominal tripping characteristic of your differential protection. What you are asked here is to say where do we start and where do we stop on our x-axis. So we'll start from 0.5 and stop at 8 times nominal current. The step, we can do 0.5, we can do much less, but I'm going to put here number 2 simply because I would like to speed up a little bit the process. If we were to say 0.5, we would have much more points, but let's say, okay, we don't have to have 2, let's have 1 here, and let's see how the test will be executed. Right now I'm doing fault on L1 on low voltage side, and by clicking OK, 8 tests are added to test list. Let's see them. So here are my tests, and when I press start, the algorithm automatically starts to generate different combinations of restraining and differential current, and we can see that we already found the first point. Now we found also now the second point, And here you can see what are our what is the IR and what is the ID, so restraining and differential current. Again, the tripping time, since we are tripping on the border itself, is not meritory for this situation. This is not the test in which you will measure the trip time. This is the test where you will be finding the threshold. But as we were speaking, we can see that the test proceeded, and right now every time you actually see the little white cross, it means that the DRTS is generating different combinations of restraining and differential current and looking for verifying the nominal characteristic. We can see now that the characteristic is actually very accurate. We have here slight discrepancy, and we can also see that on the results we have pass on all the results, and here we have error in percentages in respect to the nominal characteristic. So for now, this is the verification curve test, and the next test which I'm going to show you is going to be the test, the harmonic restraint test, trip time test, and the stability test, but we will do that in the video which comes right after this. Thank you for your attention, and make sure to watch the next video and subscribe to my channel. Thank you very much for your time and your attention, and I wish you good luck in testing. Stay safe.